Chapter 9, Counting and Probability. Pascal's formula and the binomial theorem. In this section, we'll derive several formulas for values of n choose r. The most important is Pascal's formula, which is the basis for Pascal's triangle and is a crucial component of one of the proofs of the binomial theorem. We offer two distinct proofs for both Pascal's formula and the binomial theorem. One of them is called algebraic because it relies on algebraic manipulation. The other is called combinatorial because it is based on the kind of counting arguments we have been discussing in this chapter. Pascal's formula, named after the 17th century French mathematician and philosopher, is one of the most famous and useful in combinatorics, which is the formal term for the study of counting and listing problems. It relates the value of n plus 1 choose r to the values of n choose r minus 1 and n choose r. Specifically, it says that n plus 1 choose r equals n choose r minus 1 plus n choose r, whenever n and r are positive integers, with r being less than or equal to n. This formula makes it easy to compute higher combinations in terms of n plus 1 choose r and n choose r. If they are known, then the values of this is screwed up. Oh boy. Anyway, you can, it'll show it on the, basically you can look at this triangle here, triangle structure, and if you have n on the vertical and r on the horizontal, the numbers create a triangle, and the numbers are related. So sometimes it's simply called the arithmetic triangle because it was used for centuries before Pascal by Chinese and Persian mathematicians. But Pascal discovered it independently, and ever since 1654, when he published a treatise on that explored many of its features, it has generally been known as Pascal's triangle. Let's see here. Where did it talk about that? Okay, use Pascal's triangle to compute the values of 6 choose 2 and 6 choose 3. Well, by construction, the value in row n of column r of Pascal's triangle is the value of n choose r for every pair of positive integers n and r, with r less than or equal to n. By Pascal's formula, n plus 1 choose r can be computed by adding together n choose r minus 1 with n choose r, which are located directly above and above left of n plus 1 choose r. So the sum of this value here is the sum of this value and this value. So like 10 is the sum of 6 and 4. 10 is 4 and 6. 5 is 4 and 1. But so 6 choose 2 is equal to 5 choose 1 plus 5 choose 2, which is 15. 6 choose 3 is 5 choose 2 plus 5 choose 3. or 20. So Pascal's formula, let n and r be positive integers with r being less than or equal to n. Then n plus 1 choose r equals n choose r minus 1 plus n choose r. Use Pascal's formula to derive the formula for n plus 2 choose r in terms of values of n choose r, n choose r minus 1, and n choose r minus 2. Assume that n and r are non-negative integers and r is between 2 and n. By Pascal's formula, n plus 2 choose r equals n plus 1 choose r minus 1 plus n plus 1 choose r. Now apply Pascal's formula to n plus 1 choose r minus 1 and n plus 1 choose r, and substitute into the above to obtain this monstrosity. So you notice these two elements are the same. They can be added together. So you get, combining the two middle terms gives n plus 2 choose r equals n choose r minus 2 plus 2n choose r minus 1 plus n choose r for all non-negative integers n and r, such that r is between 2 and n. The binomial theorem. In algebra, a sum of two terms, such as a and b, a plus b, is called a binomial. The binomial theorem gives an expression for the powers of a binomial, a plus b to the nth power for each non-negative integer n, and for all real numbers a and b. So the binomial theorem, you might remember from algebra at some point, college algebra at some point in the past, is this here. But you can, when you expand it out, it is a to the nth plus n choose 1, a to the n minus 1 times b to the plus or to the 1 plus n choose 2, a to the n minus 2 times b to the second, all the way up to n choose n minus 1 times a to the first times b to the n minus 2 plus b to the n. Note that the second expression equals the first because n choose 0 equals 1 and n choose n equals 1 for all non-negative integers n, since b to the power of 0 is 1 and a to the n minus n is equal to 1. Definition: for any real number a and any non-negative integer n, the non-negative integer powers of a are as follows. This is basic algebra. A to the n is equal to 1 if n equals 0, and a to the n equals a times a to the n minus 1 if n is greater than 0. Expand the following expressions using the binomial theorem. Well, just look at the first one. A plus b to the fifth is the summation of with k from 0 to 5. 5 choose k. A to the 5 minus k times b to the k. expanded out using the combinatorial notation. Multiply those out, you get this here. I'm going to skip that one. Express the following in sum in closed form without using a summation symbol and without using an ellipsis. The summation of k from 0 to n choose k of 9 minus 9 to the kth power. Well, when the number 1 is raised to any power, the result is still 1. Thus, you can write it as the summation of k with k from 0 to n choose k times 1 to the n minus k times n to the k, which using the binomial theorem works out to be 1 plus 9 to the n, or just simply 10 to the n. And that is it for that. Counting in probability, the probability axioms and expected value. Well, up to this point, we have calculated probabilities only for situations such as tossing a fair coin or rolling a pair of balanced dice, where the outcomes in the sample space are all equally likely. But coins are not always fair and dice are not always balanced. How is it possible to calculate probabilities for these more general situations? Following axioms were formulated by a mathematician in 1933 to provide a theoretical foundation for a far-ranging theory of probability. Let S be a sample space. A probability function P from the set of all events in S to the set of real numbers satisfies the following three axioms for all events A and B in S. The probability of A is between 0 and 1 inclusive. The probability of the empty set is 0. The probability of S is 1. And if A and B are disjoint, that is, if A and B are, the intersection of A and B is null, then the probability of the union of A and B is the probability of A plus the probability of B. In this section, we state three axioms, derive a few consequences, and introduce the notion of an expected value. Recall that a sample space is a set of all outcomes of a random process or experiment, and that an event is a subset of a sample space. Suppose that A and B are events in the sample space S. If A and B are disjoint, could the probability of A and the probability of B be equal to 0.6 and 0.8 respectively? It would be no, because the total would be 1.4, and that is greater than the probability of 100%. Violate the probability axiom 1. Suppose A is an event in a sample space S. Deduce that the probability of the complement of A equals 1 minus the probability of A. S representing the universal set The intersection of A and the complement of A is the null, is the empty set, is null. And the union of A and the complement of A is S. Thus, S is the disjoint union of A and A complement. And so, the probability of the union of A and the complement of A is the probability of A plus the probability of the complement of A, which is equal to the probability of S, which equals to 1. So the probability of A plus the probability of the complement of A is equal to 1. And subtracting probability of A from both sides gives the result that P of the complement, the probability of the complement of A is equal to 1 minus the probability of A. So if A is any event in the sample space S, then the probability of the complement of A is 1 minus the probability of A. The probability of a general union of two events is if S is any sample space and A or B are any events in S, then the probability of the union of A and B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. So suppose a card is chosen at random from an ordinary 52 card deck. What is the probability that the card is a face card, Jack, Queen, or King, or is from one of the red suits? Let A be the event that the chosen card is a face card, and let B be the event that the chosen card is from one of the red suits. The event that the card is a face card or is from one of the red suits is A union B. Now, the number of elements in A is 4 times 3 because there's 4 suits that each have 3 face cards. And so probability of A is 12 out of 52. The number of B is 26 because of half the cards are red. And so probability of B is 26 over 52. Finally, the number of intersection of A and B is 6 because there are 3 face cards in the in hearts and another 3 in diamonds. So A intersect B is 6 over 52. It follows from the formula for the probability of a union of any two events that the probability is 12 over 52 plus 26 over 52 minus 6 over 52, which equals 32 over 52, or approximately 61.5%. So the probability that the chosen card is a face card or is one of the red suits is approximately 61.5%. Expected value. Suppose the possible outcomes of an experiment or random process are real numbers, A sub 1, A sub 2, A sub 3, etc. to A sub n, which occur with probabilities P sub 1, P sub 2, P sub 3, etc. The expected value of the process is the summation of k from k1 equals 1 to n of A sub k times P sub k. So the expected value. The expected value of a lottery ticket. Suppose that 500,000 people pay $5 each to play a lottery game with the following prizes. 1 grand prize of $1 million, 10 second prizes of $1,000 each, 1,000 third place prizes with $500 each, and 10,000 fourth place prizes of $10 each. What is the expected value of a ticket? Each of the 500,000 lottery tickets has the same chance as any other of containing a winning lottery number. And so P of K is 1 over 500,000 for each K 1 through 500,000. Let AI sub I be the net gain for an individual ticket, where A1 is 999,995, the net gain for the grand prize ticket, which is $1 million minus the $5 cost of the ticket. A2 through A11 through A2 through A11 would be 995, the net gain for each of the 10 second prize tickets. A12 through A1011 is 495, the net gain for each of the 1,000 third prize tickets. And A1012 through 11,011 equals 5, the net gain for each of the 10,000 fourth prize tickets. Since the remaining 488,989 tickets just lose $5, the remaining A's equal -5. The expected value of a ticket is therefore A sub K, or the summation of K equals 1 to 500,000, A sub K times 1 over 500,000. Or take out the 1 over 500,000 and simply put the summation of A sub K from 1 to 500,000. That would be 999 plus 10 times 995 plus 1,000 times 495 plus 10,000 times 5 plus -5 times 488,989, or all that multiplied by 1 over 500,000. The end result is -$1.78. In other words, a person who continues to play this lottery for a very long time will probably win some money occasionally, but on average will lose $1.78 per ticket. That's how lotteries make money. And the last section, counting and probability. What the heck? Come on, be nice. All right, conditional probability, Bayes' formula, and independent events. Start with conditional probability. Let A and B be events in a sample space S. If the probability of A is not equal to 0, then the conditional probability of B given A, denoted probability of B bar A, is the probability of the intersection of A and B divided by the probability of A. So a pair of fair dice, one blue and one gray, are rolled. What is the probability that the sum of the numbers showing face up is 8? if both of the numbers on the dice are even? Well, the sample space is the set of all 36 outcomes obtained from rolling the two dice and noting the numbers showing face up on each. As in an earlier section, denote by A times B the outcome that the number showing up face up on the blue die is at A and the one on the gray die is B. Let A be the event that both numbers are even and B be the event that the sum of the numbers is 8. Then A is that set there, set of all combinations of even numbers. B would be the set of all numbers that total 8. And A intersect B is just those three combinations there. Because the dice are fair, so all outcomes are equally likely, P of A is equal to 9 over 36. P of B is 5 over 36. And P of A intersect B is 3 over 36. By the definition of conditional probability, the probability of B given A works out to be 1 over 3. So if the numbers on the dice are even, both even, the odds of them totaling 8 is 1 out of 3. Note that when both sides of the formula for conditional probability are multiplied by probability of A formula for probability of A intersect B is obtained. And by dividing both sides of the formula by P of B bar A gives a formula for P of A. So Bayes' theorem. Thomas Bayes was an English Presbyterian minister who devoted much of his energies to mathematics. The theorem that bears his name was published posthumously in 1763. Bayes' theorem. Suppose that a sample space S is a union of mutually disjoint events, B1, B2, B3, etc. to Bn. And suppose A is an event in S. And suppose both A and each B sub k, have non-zero probabilities for every integer k between, with k being between 1 and n. Bayes' theorem is this here on the board. All right. Most medical tests occasionally produce incorrect results, called false positives and false negatives. When a test is designed to determine whether a patient has a certain disease, a false positive result indicates that the person has the disease when the patient in fact does not. A false negative indicates that a patient does not have the disease when the patient actually does have it. When large-scale health screenings are performed for diseases with relatively low incidence, those who develop the screening procedures have to balance several considerations: the per-person cost of the screening, follow-up for costs for further testing of false positives, and the possibility that people who have the disease will develop unwarranted confidence in the state of their health. Consider a medical test that screens for a disease found in 5 out of 1,000 people. suppose that the false positive rate is 3% and the false negative rate is 1%. Then 99% of the time, a person who has the condition tests positive for it, and 97% of the time, a person who does not have the condition tests negative for it. What is the probability that a randomly chosen person who tests positive for the disease actually has the disease? What is the probability that a randomly chosen person who tests negative for the disease does not in fact have the disease? Well, consider a person chosen at random among those to be screened. Let A be the event that the person tests positive for the disease. B1 be the event that the person actually has the disease. B2, the event that the person does not have the disease. Then probability of A bar B1 equals 99%. Probability of A complement B1 would then be 0.01%. Probability of A complement B2 would be 97%. And probability of A bar B2 would be 3%. So, because 5 people in 1,000 actually have the disease, the probability of B1 is 0.005, and probability of B2 is 0.995. By Bayes' theorem, substituting in these values that we determined from the given information, it turns out that 14.2% of the people that have that get tested and get a positive result would actually have the disease. With the second one, a person that tests negative actually not having the disease, the probability would be 99.995% likely to not have the disease. You might be surprised by these numbers, but they are fairly typical of the situation where the screening test is significantly less expensive than a more accurate test for the same disease, yet produces positive results for nearly all people with the disease. Using the screening test limits the expense of unnecessarily using the more costly test to a relatively small percentage of the population being screened, while only rarely indicating that a person who actually has the disease is free of it. Independent events. Suppose a fair coin toss is tossed twice. It seems intuitively clear that the outcome of the first toss does not depend in any way on the outcome of the second toss. And conversely, the outcome of the second toss does not depend on the outcome of the first toss. In other words, if, for instance, A is the event that a head is obtained on the first toss, and B is the event that a head is obtained on the second toss, then if the coin is tossed randomly both times, A and B should be independent. So the probability of A bar B is equal to the probability of A, and the probability of B bar A is the probability of B. Definition. If A and B are events in a sample space, S, then A and B are independent if and only if the probability of the intersection of A and B is equal to the probability of A times the probability of B. That would be when they're independent. Let A and B be events in a sample space S, and suppose A intersect B is equal to the null. Probability of A is not equal to 0, and the probability of B is not equal to 0. Show that the probability of A intersect B is not equal to B, the probability of B, for disjoint events. Because A intersect B is not equal to 0, or is not equal, it equals the empty set, the probability of A intersect B is equal to 0. But by the probability axiom 2, probability of A times the probability of B is not equal to 0. Because neither A nor B, probability of A nor the probability of B equals 0. Thus, the probability of the intersection of A and B cannot be equal to the probability of A times the probability of B. A coin is loaded so that the probability of heads is 60%. Suppose the coin is tossed twice. Although the probability of the heads is greater than the probability of tails, there is no reason to believe that whether the coin lands heads or tails on one toss will affect whether it lands on heads or tails on the second toss. Thus, it is reasonable to assume that the results of the tosses are independent. What is the probability of obtaining 2 heads? Now, that would be 0.6 times 0.6, which would be 0.36. What is the probability of obtaining 1 head? That would be 0.6 times 0.4 times plus 0.4 times 0.6 for the two cases where one is heads and the other is tails, or 0.48. What is the probability of obtaining no heads? 0.4 times 0.4, which would be 0.16. What is the probability of obtaining at least 1 head? Well, that would be the complement of obtaining 2 heads, or obtaining no heads. So it would be 1 minus the 0.16 here, or 0.84. So 4 outcomes. Let E be the event of the head, that head is obtained on the first toss, and let F be the event that the head is obtained on the second toss. P equals P of E equals P of F, which equals 0.6, and it is to be assumed that E and F are independent. The event of obtaining heads, 2 heads, is the intersection of E and F, and because E and F are independent, it equals to P of E times P of F, or 0.6 times 0.6, which is 36%. B, 1 head can be obtained in 2 mutually exclusive ways. Head on the first toss and tail on the second, or tail on the first toss and head on the second. Thus, the event of obtaining exactly 1 head is E intersect F complement union with E complement intersecting F. Also, the intersection is null. And moreover, by the formula for the probability of the complement of an event, probability of complement of E or the complement of F is equal to 0.4. So do the multiplication out. followed by the addition, you get 48%. What is the event obtaining no heads is E complement intersect F complement. Thus, it is equal to the probability of E complement times the probability of F complement, or 0.4 times 0.4 equals 0.16. The second way to determine was the complement of the previous result, which gives you 1 minus 0.16 or 0.84. 0.84. Suppose that a coin is loaded so the probability of heads is 0.6, and suppose the coin is tossed twice. If this is experimented many times, what is the expected value of the number of heads? Think of the outcome of the toss as just 0, 1, or 2 heads. Example 996 showed that the probabilities of these outcomes are 0.16, 0.48, and 0.36 respectively. Thus, by definition of expected value, the expected number of heads is equal to 0 times 0.16, 0 heads at the probability of 6 heads, or no heads is 0.16. Probability of 1 head is 0.48, so 1 times 0.48. Probability of 2 heads times the 2 heads times the probability of getting 2 heads is 0.36, the total being 1.2. 4 conditions must be included in the definition of independence for 3 events. Let A, B, and C be events in a sample space S. A, B, and C are pairwise independent if and only if they satisfy the conditions 1, 2, through 3 below. They are mutually independent if and only if they satisfy all 4 conditions below. So, the pairwise we saw earlier, the probability of event 1 intersecting with probability of event 2 equals the probability of the first event times the probability of the second event. It just expands out with 3 different events. The definition of mutual independence for any collection of n events with n greater than 2 generalizes the 2 definitions given previously. Events A1, A2, A3, etc. to AN in the sample space S are mutually independent if and only if the probability of the intersection of any subset of the events is the product of the probabilities of the events in the subset. So, another example, tossing a loaded coin 10 times. A coin is loaded so that the probability of heads is 0.6, and the probability of tails is 0.4. Suppose the coin is tossed 10 times. It is reasonable to assume that the results of these tosses are mutually independent. What is the probability of obtaining 8 heads? What is the probability of obtaining at least 8 heads? Well, for each I, 1 through 10, let H sub I be the event that a head is obtained on the ith toss, and let T sub I be the event that a tail is obtained on the ith toss. Suppose that the 8 heads occur on the first 8 tosses, and that the remaining 2 tosses are tails. This is the event. for simplicity, they're going to write it this way. By definition of mutually independent events, the result is 0.6 to the 8th power times 0.4 to the 2nd power. Because of the commutative law for multiplication, if the heads occur on any other of the 10 tosses, the same number is obtained. Now there are as many different ways to obtain 8 heads and 10 tosses as there are subsets of 8 elements, the toss numbers on which the heads are obtained, that can be chosen from a set of 10 elements. This number is 10 choose 8. It follows then that because the different ways of obtaining 8 heads are all mutually exclusive, the probability of getting 8 heads is 10 choose 8 times 0.6 to the 8th power times 0.4 to the 2nd power, which is equal to a given number. Oh, they didn't give a result. For reasoning, for more than 8 heads, 9 heads, it's the same reasoning but with slightly different numbers. The 9th power and 10 choose 9, and P10, P getting 10, the probability of getting 10 heads is 0.6 times 10 to the 10th power, and times the number of different ways 10 heads can be obtained in 10 tosses, which is only 1. Because obtaining 8, obtaining 9, and obtaining 10s are mutually disjoint events, the probability of getting at least 8 heads is the probability of getting 8 heads plus the probability of getting 9 heads plus the probability of getting 10 heads, or roughly 16.7%. So, probabilities of the form n choose k, probability of n to the n, p to the n minus k times 1 minus p to the quantity to the k, where p is between 0 and 1, are called binomial probabilities. They don't go anywhere with that. That would be it for the slides, and that would be it for the day.